instruments used to measure ground impedance include impedance testers, earth resistance testers, and clamp-on ground impedance meters. Impedance testers, sometimes referred to as grid dip meters, measure the impedance of a grounding system by injecting a signal into the ground and measuring the resulting current and voltage. Earth resistance testers, also known as megameters or megatesters, apply a direct current voltage across the ground and measure the current to determine the resistance. Clamp-on ground impedance meters use a Rogowski coil to measure the ground impedance by clamping around the ground conductor. The procedure for testing with a clamp-on ground impedance meter is as follows. Firstly, connect the clamp-on ground impedance meter around the ground conductor. Secondly, set the instrument to the appropriate frequency, typically 50 Hz or 60 Hz. Thirdly, center the coil of the impedance meter over the ground conductor. And fourthly, record the impedance reading displayed on the instrument. The most common method for testing ground impedance is using an impedance tester. The procedure involves firstly disconnecting the grounding system from the electrical equipment, secondly connecting the impedance tester to the grounding system, thirdly injecting a signal into the ground and measuring the resulting current and voltage, and fourthly using Ohm's law to calculate the impedance. Clamp-on ground impedance meters have several advantages. Firstly, they are non-invasive because they do not require any connections to the ground system. Secondly, they are quick and easy to use, allowing the test to be performed without disconnecting the grounding system. Thirdly, they are versatile and can be used on a variety of grounding systems, including rods, pipes, and U for grounds. However, clamp-on ground impedance meters also have limitations. Firstly, the accuracy may not be as high as traditional impedance testers. Secondly, they are typically limited to a specific frequency range. Thirdly, they may not be able to measure very high impedance values. To elaborate on impedance testers, these instruments are crucial for evaluating the effectiveness of grounding systems. They work by injecting a known signal, typically an alternating current, into the ground and measuring the resulting voltage drop. This allows for the calculation of impedance, which is a measure of the opposition to the flow of alternating current. A lower impedance value indicates a more effective grounding system. Earth resistance testers, on the other hand, use a direct current voltage to assess the resistance of the grounding system. While resistance and impedance are related, they are not the same. Resistance is the opposition to the flow of direct current, while impedance is the opposition to the flow of alternating current. Earth resistance testers are useful for identifying areas where the ground resistance is too high, which can indicate a problem with the grounding system. Clamp-on ground impedance meters provide a convenient and non-invasive way to measure ground impedance. These meters use a Rogowski coil, which is a type of current transformer, to measure the current flowing through the ground conductor. By measuring the current and voltage, the meter can calculate the impedance. Clamp-on meters are particularly useful for testing grounding systems in situations where it is difficult or impossible to disconnect the equipment from the ground. When using a clamp-on ground impedance meter, it is important to ensure that the meter is properly calibrated and that the conductor is centered within the clamp. The meter should also be set to the appropriate frequency, typically 50 Hz or 60 Hz, depending on the local power grid. The most common method for testing ground impedance involves using an impedance tester and disconnecting the grounding system from the electrical equipment. This ensures that the test results are not affected by any other equipment connected to the ground. The impedance tester is then connected to the grounding system and a signal is injected into the ground. The resulting current and voltage are measured, and Ohm's law is used to calculate the impedance. Ohm's law states that impedance is equal to voltage divided by current. A low impedance value indicates a good grounding system, while a high impedance value indicates a problem with the grounding system. Clamp-on ground impedance meters offer several advantages over traditional impedance testers. They are non-invasive, meaning that they do not require any connections to the ground system. This makes them quick and easy to use, and it also eliminates the risk of electric shock. Additionally, clamp-on meters are versatile and can be used on a variety of grounding systems, including rods, pipes, and U for grounds. However, clamp-on meters also have some limitations. They may not be as accurate as traditional impedance testers, and they are typically limited to a specific frequency range. Additionally, they may not be able to measure very high impedance values. Accuracy is a critical factor when measuring ground impedance. A small error in the measurement can lead to a significant error in the calculated impedance value. Traditional impedance testers are generally more accurate than clamp-on meters because they directly measure the voltage and current. Clamp-on meters, on the other hand, rely on a Rogowski coil to measure the current, which can introduce some error. The frequency range of the impedance meter is also important. The meter should be able to measure the impedance at the frequency of the electrical system that is being tested. Most electrical systems operate at 50 Hz or 60 Hz, so the meter should be able to measure the impedance at these frequencies. Finally, the impedance meter should be able to measure the range of impedance values that are expected for the grounding system. A grounding system with a high impedance value may not be effective in protecting against electrical shock. In summary, various instruments can measure ground impedance, including impedance testers, earth resistance testers, and clamp-on ground impedance meters. Clamp-on meters offer the advantage of being non-invasive and easy to use, but they may not be as accurate as traditional impedance testers. The most common method for testing ground impedance involves using an impedance tester and disconnecting the grounding system from the electrical equipment. When choosing an instrument for measuring ground impedance, it is important to consider the accuracy, frequency range, and impedance range of the meter. Additionally, it is important to follow the manufacturer's instructions for using the meter. Ground impedance testing is crucial for ensuring the safety and reliability of electrical systems. A well-designed and properly maintained grounding system can protect against electrical shock and equipment damage. In addition to the types of instruments mentioned, another important aspect is understanding the different grounding system configurations. These configurations can influence the ground impedance measurements and how to interpret them. Common grounding system types include single-point grounding, multi-point grounding, and floating ground. Single-point grounding connects all ground points to a single location, which minimizes ground loops and noise. Multi-point grounding connects ground points to multiple locations, which can reduce impedance but may also increase the risk of ground loops. Floating ground systems are isolated from earth ground, which can be useful in sensitive electronic equipment to reduce noise. When performing ground impedance tests, it is essential to consider the specific grounding system configuration and the potential impact on the results. Furthermore, environmental factors can also affect ground impedance measurement. Soil moisture, temperature, and the presence of corrosive substances can all influence the conductivity of the soil and the resistance of grounding electrodes. It is recommended to perform ground impedance tests under similar environmental conditions or to account for any variations in these conditions. For example, soil moisture can significantly reduce ground resistance, so testing after a period of heavy rain may yield lower impedance values than testing during a dry spell. Additionally, corrosion can increase the resistance of grounding electrodes, leading to higher impedance measurements over time. Therefore, regular inspections and maintenance of grounding systems are essential to ensure their continued effectiveness. In addition to regular testing, grounding systems should be visually inspected for signs of corrosion, damage, or loose connections. Any issues identified during these inspections should be addressed promptly to prevent potential safety hazards. Grounding electrodes should be checked for proper burial depth and spacing, and any connections to the electrodes should be tightened and protected from corrosion. The effectiveness of a grounding system can also be improved by adding additional grounding electrodes or by using ground enhancement materials. Ground enhancement materials are designed to improve the conductivity of the soil around the grounding electrodes, which can lower the overall ground impedance. These materials can be particularly useful in areas with poor soil conductivity, such as rocky or sandy soils. When selecting ground enhancement materials, it is important to choose products that are compatible with the local soil conditions and that will not corrode or degrade over time. Another important consideration when testing ground impedance is the presence of stray currents. Stray currents are unwanted currents that flow through the grounding system, which can interfere with ground impedance measurements. These currents can be caused by various factors such as imbalanced loads, faulty equipment, or nearby power lines. To minimize the impact of stray currents on ground impedance measurements, it is recommended to perform tests during periods of low electrical activity and to use filters or other techniques to reduce the influence of stray currents. In addition to the technical aspects of ground impedance testing, it is also important to consider the relevant safety regulations and standards. Many countries and regions have specific requirements for grounding systems, including minimum impedance values and testing procedures. It is essential to be familiar with these requirements and to ensure that all ground impedance tests are performed in accordance with applicable standards. Compliance with these standards is crucial for ensuring the safety of personnel and equipment. Finally, it is worth noting that ground impedance testing is not a one-time event. Grounding systems should be tested regularly to ensure their continued effectiveness. The frequency of testing will depend on the specific application and the environment in which the grounding system is installed. In general, it is recommended to perform ground impedance tests at least once per year, or more frequently in harsh environments or critical applications. Regular testing can help to identify potential problems early on and to prevent costly downtime or safety hazards. The interpretation of ground impedance measurements requires careful consideration of several factors, including the grounding system configuration, environmental conditions, and the presence of stray currents. It is essential to have a thorough understanding of these factors to accurately assess the effectiveness of the grounding system. Additionally, it is important to document all ground impedance tests and to maintain a record of the results over time. This record can be used to track changes in ground impedance and to identify potential trends or problems. In conclusion, ground impedance testing is a critical aspect of electrical safety and reliability. By understanding the different instruments and methods available, and by considering the various factors that can influence ground impedance measurements, it is possible to ensure that grounding systems are properly designed, installed, and maintained. This can help to protect against electrical shock and equipment damage, and to ensure the continued safe and reliable operation of electrical systems.